Have you ever looked at a giant steel ship floating on the ocean and then watched a tiny pebble sink right to the bottom and thought, wait, how does that even work? It seems like it defies all logic, right? Well, it's all about an incredible, invisible force. So let's dive in and crack this puzzle wide open.
Okay, let's start with something you've probably felt yourself. Think about the last time you got into a swimming pool. You know that feeling? You suddenly feel lighter, almost like something is helping to hold you up. So what's actually going on there?
Well, the answer is actually way simpler than you might think. The water itself is giving you an invisible push upwards. And that upward force, that's the secret key to understanding everything else we're going to talk about.
So that strange feeling isn't just in your head. It's a real physical force, and it's got a proper scientific name. Understanding it is our first big step. We're talking about a force called upthrust.
So what is upthrust exactly? It's the upward force that any fluid exerts on an object that's in it. And get this, by fluid, we mean liquids like water, but also gases. Yeah, even the air around you. Basically, it's the universe's way of pushing back against gravity. But why? Where does this push actually come from? What's creating it? To figure that out, we've got to look a little closer at what the fluid itself is doing. It all boils down to one fundamental rule of physics. The deeper you go in a fluid, the greater the pressure gets. Just think about the crushing pressure at the bottom of the ocean. It's that same idea, just on a massive scale. Now picture an object, say a box, completely underwater. The water sitting on top of the box is pretty shallow, so it's pushing down with some force. But the water underneath the box is deeper, which means it's pushing up with a lot more force. So you've got this battle of pushes, and the simple takeaway is that the push from below is always stronger than the push from above. That difference creates an overall winning force that goes up. And bingo, that's upthrust. And this brings us right back to that swimming pool feeling. The reason you feel lighter is because that upthrust from the water is helping you out, pushing up on you and canceling out some of your actual weight. Your weight doesn't actually change, but your apparent weight does. It's just your real weight minus that helpful upward shove. Okay, so we know this force is real. We can feel it. But how strong is it? Can we actually measure it? For that answer, we need to take a little trip back in time to ancient Greece to meet an absolute genius named Archimedes. This is his famous principle, a true cornerstone of physics. And what he figured out was this. The upthrust pushing on an object is exactly equal to the weight of the fluid that the object pushes out of the way. Let's break that down, because it can sound a little complicated. First, an object goes into the water. It has to take up space, right? To do that, it has to shove some water aside. We call that displacement. Now, that water that got shoved away has weight. And here's the magic part. The upthrust, that upward force, is precisely equal to the weight of that displaced water.
I love this way of thinking about it. It's almost like the water that got pushed out is angry and wants its spot back. So it's fighting to get back in, pushing up with a force that's equal to its own weight.
So now we have all the tools. We know what upthrust is, and thanks to Archimedes, we know how to measure it. We can finally go back and solve our original mystery. Why does that huge ship float while the tiny stone sinks? Here's the big reveal, the thing that trips so many people up. It has almost nothing to do with how heavy the object is. The single most important factor is density. It's all about how much stuff is packed into the space an object takes up.
And the rules are incredibly simple. If an object is denser than the fluid it's in, it's going to sink. End of story. But if the object is less dense than the fluid, it's going to float. That's it.
And just like that, the sinking stone makes perfect sense. It might be small, but its material is packed together super tightly. Its density is way, way higher than the density of water. So down it goes.
And the ship is a work of genius. Sure, it's made of steel, which is very dense, but the ship itself is mostly a giant hollow shell filled with air. This brilliant design means its average density, the steel plus all that air, is actually less than the density of water. Plus, its huge shape displaces a massive amount of water, creating a powerful upthrust that keeps the whole thing afloat. This isn't just a fun thought experiment. Archimedes' principle is a fundamental part of engineering that we rely on constantly in the real world, every single day. I mean, we've talked about ships, but think of submarines. They are masters of this principle. pulling water into tanks to increase their density and dive, then pumping it out to become less dense and surface. It's also used in small instruments that measure the density of liquids, like milk. And it even works for gases. A hot air balloon floats simply because the hot air inside it is less dense than the cooler air outside. It's floating on a sea of air.
So think about this. The very air in the room with you right now is a fluid. It's exerting a tiny, tiny upthrust on you as we speak. And when you realize that, it really makes you wonder, what other incredible invisible forces are at play all around us, constantly shaping our world in ways we barely even notice?